All right. I'm sorry for the mistake. Last class, I didn't record the audio. I did record the video, but without the audio. So I'm going to make a brief description of what we talked on Monday. I believe we started here. We were talking about the solution of a linear system, and this is going to be the general description. But this is not a scalar equation. But here we will have a matrix n by n, and here we will have a vector of n terms. We have n differential equation and n state variable. And this is the general formulation of a linear system. We have a matrix equation here, and the matrix solution for that system is given here. So you see this exponential term. This is not a scalar equation, but this is the exponential of a matrix. And here you will have a vector with a component of the solution for each one of the state variables that we have in this vector. And here you see an integral, but again, this is a multiplication of vectors and matrices. But the integral of this will give you another vector in time, and that is the second part of this solution. So this first part is called the zero input response, because when the system has an input that is zero, this integral becomes zero. So we just have this as the solution of the state variable. On the other hand, we call these the zero state response, because if the energy is stored in all the components that can store energy in the system, that energy is zero, then the initial condition here will be zero, and this term disappears from the solution. And all that we have is the second part, zero state response. I mentioned too that in this course, we're going to focus on this because we're interested in trying to get the physical explanation of this. Why the system started from an initial condition will evolve in time until we reach the steady state. Another thing that I didn't mention, and I will emphasize that here, we will keep talking about it, but we need to find an equilibrium point for the system. So when you don't have any input, what is an equilibrium point for the system? It's a point in time that doesn't change. The state variables reach that point and will remain there forever. So if this is zero, what point is that one in time? It's a point that the derivative of the state variable is zero. It doesn't change in time. So when you don't have input and the derivative is zero, what we're going to find out is that the equilibrium point is the origin, when x for all the state variables is equal to zero. So basically, when we study the zero input response, input is zero. So we will see how the state variables will evolve in time from an initial value until they reach that 0 point origin. How further this is going to evolve? Well, that's one characteristic. It's going to decay exponentially to 0. That's another characteristic. Or it will oscillate somehow. That's another characteristic. So we will pay attention to that type of behavior, how we move from x0 to the origin. So that's what we discussed. And then we consider this example with those parameters. And in this example, you have just one component that stores energy, this one. The input is going to be 0, so we will put a short circuit here in this source, and we will see how this circuit will change, starting from an initial condition that is 50 volt here at this time. So we will see how that voltage will change from that value in time. The steady state value for the voltage, because there is nothing else, it will be 0. So we want to know how that voltage will change in time to 0. But because this is a scalar system, actually we can get also the zero state response, which is when we include the source. The equation that we get is so simple. It's just one equation. We can solve it. It's easy. And that's what we have here. So the zero input response is discussed here. We talk about this last class, but basically it's just solving this simple equation, which is a scalar. This coefficient here will give you the rate of change. What is the time constant of this exponential decay? And the solution is right there. So 1 over RC is going to be training this case. And the second part, which is the zero state response, will have to do with solving the integral. Because the equation is not a matrix equation anymore, it's a scalar equation. We can put the coefficient of this equation right here and solve for the integral. There are some algebraic manipulation we need to consider, but we can prove, and this is fully in the notes, so go step by step in the notes. We can prove that the solution for this is this expression. So when we combine the two solutions, the zero input response and the zero state response, then we will have the full solution for this RC circuit, which is plotted here. That full solution is a line in black. So we start from 50 volts here, and this is how the voltage in the RC circuit will change in time until we reach a steady state. And in this case, the steady state behavior is sinusoidal because the input in the system is a sinusoidal source. If we just consider the zero input response, we will have the curve in red, which show in this case that you have a change from the initial condition, and it will decay exponentially until we reach zero. That's the natural response of this circuit. What is the purpose of this problem? Is just to show completely what is the solution of any linear system. In this case, it's just one variable. Now, the same idea will be expanded when you have multiple state variables, multiple components that can store energy. But the solution of the zero input response is going to be more difficult to get. How we're going to do it in the future? We're not going to get an analytical solution for the zero state response, but we're going to solve it numerically. We will use a computer, and I will explain that in a chapter later, how we get the full solution, this black line here for any system. So we will get there. And again, chapter 2, what is the purpose? It's to study this response that is described by the red line. We want to understand that for any system, in this case it's one state variable, but how it would be for two state variable or more, we will understand that by using eigenvalues and eigenvectors. Yes?
So for any stable system, will, like after a long amount of time, will the combination of the zero input and the zero state response always like match after a long amount of time? Like on here, we see that the combination of the zero input response and the zero state response, it dies into the form of the zero state response. Is that always true for every stable system?
For a stable system, the zero input response will vanish always.
Yeah.
And that's what we want. And that's why you see this evolution until we merge into the steady state behavior that is given by the zero state response, okay, given by the input of the system. Yes. So that's what we talk, and then we start talking about how we understand this. And one of the mathematical definition we need to understand this is eigenvalue. But eigenvalue definition will go along with eigenvectors. So how we understand this, and this is something you study at the beginning of the program, but here I'm trying to give you a graphical description of what is an eigenvalue and eigenvector. And this graphical description has to do with the linear transformation. A matrix, any matrix, can be seen as a transformation. If you take a matrix and then you multiply that matrix by x, so this matrix will be transforming that vector x into something else. Y will be a times x. We are transforming that vector, and that is the example right here, which is plotted here. If you have this vector x, when you have ax, then you get a different vector y. So that will be the general case for any matrix. But for any particular matrix, we are able to find singularity situation, singular situation, in which this transformation is unable to change that initial vector x. That is the definition we get. In this case, this is the definition, mathematical definition you have for an eigenvalue and eigenvector. So if you have AQ, where Q is the eigenvector, this must be equal to the same vector scale with this eigenvalue lambda. So basically, when we look at the transformation here, this is a particular direction in that space. The matrix is 2 by 2 in the previous page. So in this R2, the plane, we're finding a particular direction in which that matrix is unable to change the direction of this vector, and we lay in the same direction. So that's a singularity, a singular. And for this case, this is one direction. This is an eigenvector for the matrix that I showed you before. So if we get the multiplication of A times X, what we get is this expression. So we can factorize this by this scalar, and we get exactly here the same initial vector X. So A times X is nothing else than the same X scaled by a given number. This scaling factor is called the eigenvalue, and this particular direction is called the eigenvector. Because we're in R2, we will have two specific directions in which we're going to have this situation. This explanation is given when the eigenvalue and eigenvectors are real. And this is a general case. So for that matrix, if I can start, I change the input x, and I pick any value along this circle. In this case, I have this value, and this is the y that I get. But if I start changing this x for any other point along the circle, and if I can plot all the output that I get, which is a y, I get this red trajectory. So for any vector in the circle in blue, I will get a vector in the ellipsoid in red. So basically, this matrix A is transforming the geometry of our system. So if you have a circle and you pick any x within that circle, you obtain an ellipsoid. The ellipsoid will have an area in which the circle is stretched to the maximum here. That stretch is going to be characterized by a large eigenvalue. Yeah? And then you have another part here, which is in the direction of Q1, in which this transformation is compressed. So then, along the Q1, we will have an eigenvalue that is going to be less than 1. Another observation that we have, I think that you mentioned that, right? That the direction in which x and y point are different for the case of Q1. So in that case, the eigenvalue will be negative. So when you have x pointing in this direction, y will point down. So the eigenvalue will be small and negative. For the other case, x and y will point in the same direction. So the eigenvalue will be large and positive. We got this in MATLAB, and I asked you to play with the MATLAB code that I put in Canvas, and you need to play with it. Did you get anything different? You were going to play with that. What were you going to do? Change the matrix. Use something else. Were you able to do that? Do you have anything meaningful you found?
I found one in one case. So in the picture you have on the slides, the eigenvectors are roughly perpendicular to each other. And depending on the transformation matrix, sometimes they're closer angle, sometimes wider. And then in one case, they were completely 180 degrees from each other. So the red oval was just a line with no width. It was just
really?
a line, yeah.
Do you remember the matrix you?
I did it and then I changed it and I kept trying to remember. It was random. I randomly.
So what we can do also in Canvas, there is a section that is discussion. We can open a discussion. Any one of you can open a discussion. And why don't we use that? And maybe David, can you do that? Put that case you found and put it there, and let's talk about it. Yeah? So we will discuss that. In this part, because I just gave you the graphical description of what is an eigenvalue and eigenvector, in this part, we're going to start talking about a new concept, which is the one that we're going to use to find the solution of this dynamic linear system. And that concept has to do with diagonalization of dynamic systems. We're going to get there. I think we finished here last time. So what I have here is actually the singularity, which is the definition of eigenvector and eigenvalue for this matrix. It's a particular direction in the space in which we have this singularity. This transformation is unable to change the direction of Q, and we have as an output something that is proportional to Q only. And as I said, because we have an n-dimensional space, we have n state variables, then we should be able to find n eigenvectors and eigenvalues. So we're going to assume here that all of these are different. All lambdas are different and all q's are different. That's the assumption we will have in this course. Can that assumption fail sometimes? Yes, it can fail. And when that fails, when you have a repeated eigenvalue, the dynamics of the system will be very particular. We will skip that part. Why? Because in the power system, it's very hard to find that situation in which you have eigenvalues that are repeated. Most of the time are going to be distinct, different. So that's what we're going to assume here. So if you have an equation like this, you have for each pair of eigenvalues and eigenvectors, and these eigenvalues and eigenvectors are all different, what we can do, first of all, we can write this in a different fashion. We can send this to the other side of the equation. We can factorize by qi, and what we obtain here is actually this to be 0, because q is a particular direction. It cannot be the origin. This cannot be 0. So the only way that this is equal to 0 is if this matrix here is singular. How we understand this Q, and this is something I was talking last time here. Stop sharing. It work. Is it working? Yes. So that equation right there can be understood in the same fashion, in this fashion. So you have a matrix A, and you have X. What is the meaning of that? Well, we can expand this matrix A into their columns. Let's say A1 is the first column, A2 is the second column. Let's consider that A is the 2 by 2 that belong to the real. So if you have this situation, then the first component of X will be X1, and then you have X2. So when you do this multiplication, basically what you get, and maybe let me expand this. And here this is a A1, which is the first column. But let me put a second number here. A11 is the first term of that first column, and A12 is the second term of the first column. And this one is going to be the first term of the second column of A, and this is the second term of the second column. So if I have that and I do this multiplication, we get A11 X1 plus A21 x2, and in the second row I get A12 x1 and A22 x2. So here I can separate this and I can factorize by x1 and x2. So one component can be this one, and the second component can be this one. I am just separating this result. AX is a vector, and that vector is obtained in the traditional way by multiplying this matrix and this vector, you get that. But we can separate this. And what you see here, this is the first column of A, and this one right here is the second column of A. So basically, what is the meaning of this? When you have this product here, basically what we're doing is getting a linear combination of this matrix. And the coefficient of that linear combination are in the terms of X. So X1 is the factor that will multiply the first column, and X2 the factor that will multiply the second column. And this is a linear combination. That result is a linear combination of the columns. Now let's go back to what I said before, that we have a very particular situation in which we have lambda I minus A, and this is for an eigenvalue lambda I, and this is multiplied by Qi and equal to 0. Qi cannot be 0 because this is a specific direction in the space. So the only way that this is equal to 0 is if the column of this matrix are linearly dependent. Yeah? When you have linear dependency, remember that part? For example, in this case here, you have a linear combination of the columns. If these columns are linearly independent, there is no way that this sum will lead to 0. You remember that part from linear algebra? So if this is different than 0 all the time, it's because the column of first column and second column of this matrix are linearly independent. But if these are 0, it's because these are linearly dependent. The second column is just some scale vector of the first column. That's linear dependence. That is exactly what we're getting here. So to find this singular direction, which is the eigenvalue, we need to enforce that this matrix lambda I multiplied by the identity minus A must be linearly dependent. So these need to be singular. Is this something you remember from before? Do you remember linear dependency, independency? Yes. So when this is singular, that's the same thing than saying linearly dependent. The columns of these are linearly dependent. Yeah, let me share this thing. Yeah, so we are back here. Let me change the camera. Okay. Yeah. Okay. So that's what we have here. So to find the singularity, these need to be singular. So how do we determine when a matrix is singular? There must be some linear dependency, but mathematically, we can immediately find linear dependency if the determinant of this matrix is 0. So that's what we're enforcing. We're saying we want to find this direction with that scaling factor, but to find that direction needs to satisfy this, that the determinant of this is 0. So if we do this, what we're going to find out is that when we do this, actually, we will get an equation that looks like this. And this is the coefficient of this equation. You see this coefficient here? Correspond to the same coefficient of that n-order differential equation we started talking at the beginning of this class. Remember, for the RLC circuit, you memorize some second-order equation for that circuit. The coefficient of that second-order equation will correspond to the coefficient that you get in this characteristic equation. So that characteristic equation can be obtained using that n-order differential equation, or can be obtained by solving this determinant and making the determinant equal to 0. You will get the same thing. So what I am saying here, something that you studied before now can be expanded to any system without knowing that n-order differential equation. These are a set of linear differential equations. If you solve this, you will get the characteristic equation. Yeah? So to find that eigenvalue, we need to solve this for any system. And when you solve that lambda, then what we need to do is to replace that value here and find the direction that makes this equal to 0. That's the procedure. And here we have two examples, and let me go back here, and we will work on that. Let's work on one of them, and see what we get. So sharing, there it is. So the first one is A1 that's a matrix. Yes, that's a matrix. Now we need to find the eigenvalues, but the eigenvalues will be determined by finding the lambda that make this determinant equal to 0. So the matrix that we have is lambda. That's the first matrix here, minus A and we can subtract those two matrices and we get lambda plus 3. The negative sign gets canceled here. And here you have negative 1. And I'm sorry, this is lambda. And this is. So we need to get the determinant of this matrix. So the determinant for this 2 by 2 matrix is obtained by multiplying the diagonal terms. And subtracting this product of the off-diagonal term. So it's the negative of negative 2, which is plus 2. And these need to be equal to 0. So we can multiply the terms here, and you get lambda squared plus 3 lambda plus 2 is equal to 0. So that's a quadratic equation we can solve, and we know how to solve because we have an analytical expression for this. The solution typically consider A lambda squared plus B lambda plus C equal to 0. These are the coefficients of this equation. So A in this case is 1, B is 3, and C is 2. And the solution for this is going to be negative B plus minus the square root of B squared minus 4 times AC divided by 2A. So we replace that there, and we get negative 3 plus minus 9 minus 4 times AC. And you get 4 times AC. You have A there. And this is divided by 2A. A is 1. We get that. So in this case, what we get is -3 plus minus 1 divided by 2. So this would imply that one solution, lambda 1, is going to be -3 plus 1. That's -2 divided by 2 is -1. And the second solution, when this is negative, then you have -4 divided by 2, which is -2. So we have two eigenvalues for that system. Do you remember this? Yeah? Now we need to work on the eigenvectors. So for each one of these eigenvalues, we need to replace that in our equation of the singularity, and we need to try to figure it out. What is that direction that we will have a singularity? So for the eigenvectors then, we start with the first eigenvalue, which is -1. And what we have here is that lambda 1 minus A multiplied by Q1 is equal to 0. That's the singularity. We know how much is lambda 1. So now we need to determine how much is Q1. So if we replace this in our matrix, lambda 1, which is -1, we get, the matrix is, let me put here the matrix again. It's -3, -2, 1, and 0. So this is going to be -1, and then you get 2. You get 2. Here you have -1 and -1, and this is multiplied by Q1. We can define Q1 as a vector that has the first and second component, and this needs to be equal to 0. So what do we observe here? That is singular. What is the meaning of the system of equation being singular? You have one equation that is linearly dependent with the other. So if you get the first equation here, how much do you get? 2A plus 2B equal to 0. If you have the second equation here, the second row, you have -A, -B equal to 0. These are linearly dependent, right? So you only need one equation. The other is the same equation that is being scaled. So the solution here, we can conclude that the direction of the eigenvector for lambda 1 is 1, in which we have that A is equal to -B. This is singular. All that we need is that relationship. In which direction in the plane this needs to go? Well, if you have B, then A needs to be -B. So if you plot this in the plane here, you have x1 and x2. What that direction is? It's a line. That's the one? No, it's negative. It's something like this. So if you have A, then B is going to be the negative. So here I can pick, because we're interested in the direction only, we can pick B equal to 1, and then A will be -1. So from here, we conclude that the direction for this can be, let's say B is -1, then A is going to be 1. That's the direction. And we pick another value for this. Let's say that B is -2. Then the direction will be 2, -2. Can that work too? Yes, it can work. Anything that will satisfy this main relationship. So we will do the same thing now with the second eigenvalue. So this is going to be lambda 2. This is negative 2. And then you have negative 2 plus 3. That's 1. These are the same. And this change to negative 2. Do you see the relationship? Again, this is singular. The second equation is exactly the same than the first one, but multiplied by negative 1. In this case, then, let's put here Q1 is 1, negative 1. So from this relationship, we get A, the first equation only, A plus 2B equal to 0. So here, A will be negative 2B. And from here, we can conclude that Q2 is going to be, if B is negative 1, then A will be 2. So Q2 will be 2, negative 1. And once again, can we pick a different vector? Yeah, we can say that B is 10. Then A needs to be negative 20. It doesn't matter the magnitude of that vector. All that what is important here is the direction. In that direction, then we will have the eigenvector related to lambda 2. What I'm going to ask you to check the eigenvalues of the second matrix. Let me go back there. Share this. There it is. And then to go back here.
I have a question.
Yes.
The matrix, there was like 2, 2, negative 1, negative 1. Did you just subtracted A from the eigenvalue, right?
Yeah, I am doing this equation right here. Lambda I minus A. So I replace here lambda 1, and then I did it for lambda 2. But then I need to get this subtraction of these two matrices. That's the result for lambda 2.
So like, so you would take negative 2, like plus 3, plus 2.
Yeah,
minus
negative 2 plus 3 will give you 1.
Right.
This is the negative of that off diagonal term in the matrix A, the same than this, the negative of that off diagonal term, because we're subtracting A. And this is going to be lambda 2 minus 0. You want me to do it again?
Just I guess I don't get how you got the 2 and the negative 1. I get the 1 and the negative 2. You just negated them.
I will do it right here.
Okay, got it.
And let's do it one more time here. So for A, we're using A1, which is negative 3, negative 2, 1, and 0. And we need to get the second eigenvalue multiplied by the identity minus A. So this is going to be lambda 2, 0, 0, lambda 2, and the negative of this. So we need to change the sign here. It's going to be, let's change the sign here,
Right.
plus 3, plus 2, negative 1, and 0. So lambda 2 is negative 2 in this case. To have negative 2 plus 3 is 1. This is going to be 2. This is going to be negative 1. And this is going to be lambda 2, which is negative 2.
I just missed the part where it was like the 0, so we're good. Thank you.
So what I'm going to ask you to work on the complex case, which is this one. If you try to determine the eigenvalue and eigenvector for this, they are going to be complex. Please check the appendix of the notes. The full solution is there. What I want you to do, work on that, try to understand how you get it, and render question if you cannot find the solution.
I have a question. Doesn't whether the eigenvalues are real, complex, or repeated, doesn't that have something to do with the equilibrium of the
Has to do with
system?
the system itself, the interconnection of your component and what component you have there. That's all that is there. So the capture mathematically these values for lambda and q will describe exactly that interconnection in components you have. That's why in an RLC circuit, we will find most of the time that the eigenvalues are going to be complex. We will get there. We're not there yet, but we will understand why they are complex. So now that we review how to determine the eigenvalues and eigenvectors, what we can do is to put all the singularity equation together. So you have, in this case, one equation for the first pair of lambda 1, q1, and the second, all the way to the last one. We have a system with n state variables. So each one of them needs to be satisfied. So what we can do, because they all depend on A. A is capturing that characteristic of that system. All depend on A. So when you do this product, what do you have here? A column vector, column vector, column vector, column vector. All of these are column vectors. So what we can do, we can put them all together. So in the first column of this set of equation, I'm going to put this equation, AQ1, this is a column vector. And what I'm going to put here, this one. So this is an equality, right? A column vector. Second equation, I will put the second column here, AQ2. And here I'm going to put this one. This is an equality. And I will continue in that fashion until the last column, AQN, lambda QN. So this is an equality. We haven't done anything different. We're just putting all of these together in matrix form. Because you have n column equation here, now you have a matrix m by n, all together. It's just one equation for all those n singularities. So what we can do here, we can factorize by A from the left. I can take this A out of this matrix, and you get something like this. A multiplied by this new matrix that we're going to call capital Q. Each column of capital Q will correspond to each one of the eigenvectors, AQ. And what do you get on this side? Well, the first column is going to be Q1, but multiplied by lambda 1. The second column is Q2 multiplied by lambda 2, and so on until the last column. So that can be factorized in a very particular fashion from the right, where this matrix now is a diagonal matrix in which the diagonal term corresponds to the eigenvalues. So if you do this multiplication here, the first column always, you see, the first column will be always multiplied by lambda 1. And when you do this product here, you get lambda 1 Q1. The second column of this product will always be multiplied by lambda 2. So you will get Q2 lambda 2, and so on. So basically here, we arrive to one matrix equation that involves all the singularities. And this matrix equation tells me that A times Q is equal to lambda. So mathematically speaking here, you have a one-to-one correspondence between this matrix and this matrix. What is that matrix? That the system matrix can be a matrix with some terms and can have any order depending on the system. But what is this matrix? Oh, very particular matrix. It's actually a diagonal matrix in which the diagonal term corresponds to the eigenvalues. So we are finding here a relationship between the system matrix and this diagonal matrix. So far, it's just a compact equation based on our understanding of this singularity, the eigenvalues and eigenvector. We put everything in one equation and we arrive to this nice relationship. We're not there yet, but we're getting closer. So we will use this to solve the solution of the linear system. Another way to express this relationship, because this Q, the column corresponds to the eigenvectors. So each one of these directions, we said that they're different. In the space, you will have directions that are linearly independent. Because they are linearly independent, this matrix Q will never be singular. And because this will never be singular, that means that the determinant of this is never 0, right? And what does it imply? That implies that we actually can get the inverse. What is the inverse of a matrix? Remember the equation?
1 over determinant something.
Multiplied by the join of the matrix. So if the determinant is 0, what do you get? Infinite. You cannot get the inverse. Yeah? But by this, because these are eigenvectors, the determinant of this matrix will never be 0. Therefore, this is invertible. We can get the inverse of Q always. So if we can get the inverse of Q always, I can multiply from the right by Q inverse. So you get A, Q, Q inverse. How much is Q, Q inverse? Identity. So basically you get A. And that needs to be equal to Q lambda Q inverse. So we have an equation for A in terms of lambda. The same thing I can do from the left. I can multiply by Q inverse from the left. So if you do that, you have Q inverse AQ must be equal to lambda, because Q inverse Q is the identity. So by doing that, because Q is invertible, we establish these two relationships. Yeah? So what we're going to do now, we have like 2-3 minutes. We're going to use this matrix Q to redefine the variables in the system. We're going to make a transformation. Why we're going to use a transformation? Because that will simplify the system representation. If we are able to have this transformation, and this is the main concept of this part, we have just discussed the mathematical implication of these eigenvectors and eigenvalues. But now we're going to have a practical implication of this, which is the following. You will have the state space representation here with some initial condition. We have a system. We discussed already we can get this for any system. So what we're going to do, we're going to transform this into a new representation. Why we're going to do that? Because we believe that in this new representation, we can find a solution easily. These variables are going to be converted into a different variable, y. And we're going to get the solution of this y. But when we get the solution, we're going to transform this back to the original system. So we will define this transformation using this matrix Q, just to find a different representation that is simple, that we can find a solution for that. And when we get the solution, we will transform the solution back to the original system to finally know how much is the solution for all the state variables for all t greater than t0. So we're going to do that next class. To summarize what we did today, we discussed about eigenvectors and eigenvalues, and we have some exercise here, and you need to study the second matrix. The second matrix will be complex. Go and check the appendix of the notes. You will find the full solution there. But try to understand how to solve it. Bring your question if something is confusing. And then we formalize these singularities and put it all in a single equation. You get this matrix capital Q. We will use that on Friday to find this transformation and transform the system, solve it, and transform it back to the original system. So we finally will know how to get the solution for any linear dynamic system. Yeah, this part is going to be very mathematical, but you need to hang in there because soon we will be applying this to the power system. That's the goal. Okay. Yes.
So
Question.
this diagonalization only can happen if the vector of Q's is linearly independent, so no repeated eigenvectors. And
Eigenvalues.
eigenvalues. So in a system, a real-world system, like a power system, it's rare to have repeated.
It's very unlikely we will have repeated eigenvalues.
So that's why
When you have eigenvalues repeated, that is a very particular dynamic response that has to do with the structure of the system. I have never seen that situation in a power system. When you have repeated eigenvalues, mathematically, you can still get linearly independent eigenvectors. We will not talk this here, but that is called the Jordan form. So if some of you are planning on going into the grad program or are already in the grad program, you might hear that term in grad courses, the Jordan form. That's the generalization of these two repeated eigenvalues. Yeah. Okay. Thank you, guys. I will see you on Friday.